Hello, this is the next video in a playlist that I'm calling hypothesis testing, and here we're in the unbiased hypothesis testing phase. Specifically, we've looked at uniformly most powerful unbiased test when it was simple versus composite hypotheses, and now we're doing UMPU composite versus composite tests, and here we're going to look at the normal variance. So in the previous video we derived the theory and a little bit about how we're going to find the critical region in these tests, because it's not straightforward, it's not easy. So this video is the same title, but it says using R. So let's just jump right in. Oh, maybe I should say the hypothesis, the null hypothesis, is that sigma, the true normal, the variance of the normal distribution, is between two values, sigma 1 squared and sigma 2 squared, or is it strictly less than sigma 1 squared, or is it greater than sigma 2 squared? So we are going to assume that we're testing sigma 1 squared of 9 and sigma 2 squared of 11. So is the true variance between 9 and 11 or not? We're going to do a sample size of 55, alpha 0.05 test, and the two equations that we developed in the preceding video of this playlist set up two criteria. And one was this, where we had equations for C1 and C2 values, and then we had another criteria, the expected value of the test function under the sigma 2 squared. It creates this set of equations. And so what I want to do is plot these and show you exactly what's going on. So this is the plot of the first equation. So these are the C1 and C2 values that make that equation true. These are the only ones. Now let's plot the equation for the second equation, and then all possible C1 and C2 values that make it true. And that's this red line here. So you can see that there's only one dot, one point, that makes both of the equations true. And then that's the point we're looking at in the critical region. The C1 and the C2 that make both of these true is the uniformly most powerful unbiased test for this setting. So what we do is we just create a function, and we create this function and subtract off this function. So we make it a function of C1, and then we subtract the C2 values, and then when they're equal, we know we have the solution. So that's what this equation does. The function, I just create a function where I subtract the two functions. Then I take uniroot and I solve for C1, and that's it. So we have the C1 value, and then once you have C1 you can kind of back solve for C2 very easily. So now let's plot that point that we just solved for, and I don't know if you can see it on my screen, but there's a circle around that point. And that's what we just solved for using uniroot, is this value right here. But I like the lines, because then you get to see exactly what we're doing or what we're solving for. So now once we have the critical region, C1 and C2, let's create a power function using the critical region 1, that's the left side, critical region 2, make it a function of the variance, which is where S is, and then we plot it. And here it is. Here's the power curve. Remember, the null hypothesis is the variance between 9 and 11, and so that's these vertical dotted lines. Notice that the test function, or the power function, is at 0.05. That's a horizontal line. Below it, in the the null region, and in the alternative region, it's above alpha. So it is an unbiased test, and it turns out to be UMPU, in this testing setting. so that's it. So now let's do a little computer simulation. Let's do 1 million replications. Let's assume the true variance is 16, and let's create a matrix that has 1 million rows and 55 columns, because we're using a sample size of 55 still. So that matrix, each row represents a sample of size 55. The test statistic is the sum of the x squareds. So we square each element and then take the row sums and put it back in x. And that frees the memory from that 1 million row matrix. And so now x is a vector. It's a 1 million length vector by 1. So then we see how many times it's above and below the critical region. We table it, and then we probably should just divide it by the loops, and that's the simulated power. And let's plot that in the power curve to see if it is close. So we assume the true variance is 16. We did 1 million replications using the critical region that we derived, and the simulated value was 63%, which is right on the theoretical power curve. And with 1 million replications, I'd be so surprised if it wasn't pretty much on that equation like it, or the power curve like it is. So now let's do the leave out one side test. And it's basically, if you assume you're in the alternative region, on one side, then the other side, the probability of being in that critical region is really small. So why not leave it out? And then calculating the rejection region is so easy. So this is it. CR1, leave out one side. That's the critical region on the left side. Boom, we're done. And the critical region on the right side, that has to be alpha, and we're finished. And now if we look at these two regions, so 349.2 versus 350.6, they're very close. The UMPU test on the right side is 813.5, and the leave out one side is 806. So they're very close, very similar. I know. I had a brain cramp there. So what I plot is the density of the chi-squared that we're looking at. And then I plot the critical region. So the red is the UMPU test. And then the blue is the leave out one side test. And this is it. And so you can tell that the critical regions are very close. But let's look at the power curve. So let's find the power curve for the leave out one side test. And let's plot them right on top of each other. The uniformly most powerful unbiased test and the leave out one side test. And look at them. And if you can see that they are so close. On the right you can see there's a little bit of a gap, but it's right on top of each other. So this is an approximate uniformly most powerful unbiased test. The leave out one side test is. Well, that's all I have for this. As all my videos with R code, I copy and paste the code into the comments. I'll try to pin it so it stays at the top, so you can copy and paste it into your R program. That's all I have. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.